All right, in this video, we're going to go over just a little bit of Laplace transform and region convergence stuff. There was a little bit of confusion about it, so I'm trying to clear it up. This table information right here is right from table 9.2. So it gives a signal of e to the negative at times a unit step, and it is the Laplace transform is 1 over s plus alpha. I guess this is an alpha. And then the region of convergence is that sigma is greater than negative alpha. And sigma is the real part of S. That's right there. Okay. And then the second signal, negative E raised to the negative alpha t power times a anti-causal unit step. So I call this anti-causal because it is going this right here is going to evaluate to 0 if t is greater than 0. And here's our transfer function h of s right here. Okay, so from this, we can get information about our poles. Our poles occur, and if we could write that this is the numerator as a function of s, and the denominator as a function of s. Poles occur when h of s goes towards infinity, which that implies that as d of s goes to 0. So we want our poles will be zeros in the denominator. And so we just need to solve. We have s plus a equals 0 and s minus b equals 0. So that means that s is going to equal negative a and s would equal b. So those are our two poles. So we can, I got 3 axes here, or three sets of 3 s-planes. So we'll mark one here. This is negative a, and that is a pole. And then right here we have b, and that is a pole. And we'll do the same over here. Negative a and b, and then negative a and b. Right about there. Okay. And we could have, there's 3 possible regions of convergence here. So this S-plane, we're going to have an LTI system, a linear time invariant system. Now, if we say that the system is linear and time invariant, that means it is a causal system. If it's a causal system, that's going to imply that we are talking about a normal unit step. There could be a time delay or whatever, but we're not going in the negative t direction. And when we have something like that, when we have an LTI system, meaning it's causal, and we have a normal unit step, we're going to have a right half plane region of convergence. So if I draw these dotted lines here, here's one pole, here's the other pole. All right, and the region of convergence cannot contain any poles. So if we have a causal system, well, that means we're going this way. We're going this way from this pole, and we're going from this pole, we're going to the right, and we're going to the right, and the region of convergence cannot contain any poles. So right here, our region of convergence is the right half plane. It is everything over here. And you can see that right here from table 9.2. So the region of convergence for this one is going to be that sigma is greater than b. Now, let's suppose we have an anti, or we'll do stable. We'll do stable first. So this would be if the system is stable. Now, in order for the system to be stable, the j omega axis has to be in the region of convergence. Okay. And the region of convergence cannot contain any poles. So that means that at A, we must be going to the right. So A is a right half plane. The pole at the signal associated with the pole A, or the pole at negative A, is going to be a causal signal. So right here we can write the U of t. This is going to have a region of convergence of sigma greater than negative A. And then if we contain the j omega axis, then that means that the signal associated with the pole at B must be going this way, must be going back. So this is going to correspond to a U of negative t. And the region of convergence for this signal is going to be sigma is less than B. And okay. And these are linear operations. So here's our region of convergence for this one. This is a strip in the S-plane, and it contains the j omega axis. And don't forget, if we did have some signal, let's just say x of t. Well, x of t is a signal, right? But x of t could be a superposition of two other signals, x1 and x2 of t. This is a signal, but this is also a signal, and this is also a signal. So that's why I say the signal, the signal that is associated with this pole here, or the signal associated with this pole here. It's just those two make up. If this one was x1 and this one was x2, these two signals will make up another signal when you add them. All right, now let's, there's the third option for the region of convergence here, is if the signal is neither stable nor causal. Let's write a star over here. This is a causal system. And we'll say, well, this is an anti-causal system. Anti-causal, not stable. Right? If it's anti-causal and it's not stable, well, if it's not stable, the j omega axis is not included in it. If it's anti-causal, that means we're not right half plane. Let's write right half plane here. If it's anti-causal, we're going to be left half plane, which means that the signal associated with the pole at negative A is going to be anti-causal, right? And the signal associated with the pole at B is going to be anti-causal. Oh, I forgot that negative sign in there. And because the region of convergence cannot contain any poles, well, that means that this is our region of convergence out here. So we have a region of convergence of sigma less than negative A. And we could rewrite the region of convergence over here for this one. So let's move this down. Let's move this down, right? So our region of convergence, we could write it out as one thing. The ROC, the region of convergence, is going to be negative A is less than sigma, which is less than B, right? Because here's negative A and here's B, so we're going to be in here. We're going to be in this region somewhere. We're going to be greater than negative A, and we're going to be less than B. Okay. Now we can get the transforms for these two. So let me try to get a little room in here. Let's move this down right there. Let's move this right here. Now we can, let's put this there. Let's put a box around it. So we want to get this into some form that looks like something from the table. It means we should have something that looks like this and something that looks like this. And there's a couple different ways you could do the partial fraction expansion. And here's the easiest way. Well, to me, is you just write A over S plus A plus, and we'll do capital B over s minus b. And now we can figure out those coefficients, and we'll do that in a minute. But right off the bat, this is what this looks like. This is a times 1 over s plus a plus b times 1 over s minus b. And now that it's in this form, I can look back and I can see, well, here's what it looks like, right? So alpha in this one is going to equal alpha is going to equal a, and alpha in this one is going to equal negative b. So when I take the Laplace transform, and we'll do it for the causal one first. All right, so when I take the Laplace transform, or the inverse Laplace transform of this, I'm going to have a, and I take the inverse Laplace transform of 1 over s plus a, and that looks identical to this with the substitution of alpha, but I get e to the negative a t u of t. And then I take the inverse Laplace transform of the next term, and I get b times e to the negative b of t u of t, and this is the negative times the negative, and I just wrote it out so that way it was nice and clear, but that's just going to be b t u of t, right? And we could factor out that u of t if we wanted to, but I'm just doing it term by term. And this is a causal system. We're going in the positive time direction, right? And we can see why it's unstable, because if we take the limit as t goes to infinity of as t goes to infinity, h of t, for this first term is going to go to 0, but the second term we're going to have an exponential being raised to some infinite power, so that's going to be infinity. And that's why it's not causal. Now, for the stable system, let's try to box this off. For this, okay, now we're going to look at our stable system. So if we're looking at our stable system, we're going to have a Laplace transform, right? And our signal associated with the pole at negative a is a causal signal. So that's not going to change from our linear time invariant one. We'll have this same thing right there. So we can just go ahead and write that down. Now we have a times e to the negative a t u of t, right? And let's take a look at this real quick. So this is b times 1 over s plus a negative b, correct? So negative b is our alpha that's up here. And we see that the only thing that changes is really this minus sign there. So we, instead of writing this plus sign here, we'll just write our minus sign. So we have minus b, and then it's e to the negative b t u of negative t, because that's what our Laplace transform table says, right? And we'll clean it up real quick because we don't need that negative, but that's just going to be b t u of negative t. And if we take the limit of this as t goes to infinity of h of t, well, let's just let's say we plugged in what would be h of 10 to the 6. Well, that's going to equal a times e to the negative 10, or excuse, negative a times 10 to the 6, which is going to be essentially, that would essentially be 0. And this right here, this unit step at that point will be evaluating at 0. So the limit of h of t as t goes to infinity is 0, which is why it's stable, okay? And the j omega axis is included in this because it's stable. All right, and we'll do our last one now. And this is the anti-causal, and it's not stable. And you should be able to just kind of pick up on this right now. It's gonna, we know the second half. We know the second half of it, meaning our signal associated with this part of the transfer function here. Well, that's going to be minus b e to the bt times u of negative t, because it's just going to match this one that's right here. And then all we have to do for this other one is we add the negative sign in front. So we have negative a e to the negative a t u of negative t. And that's what it's going to look like. And if we took the limit as that, as t goes to infinity, well, we're going to get infinity. This term here would go to 0, but this term right here, we're going to have a, I guess I should have put the limit as t goes to negative infinity. I apologize. The limit as t goes to negative infinity, we're going to get infinity. Because if we put a negative infinity in here, if we put a negative very large number in here for t, then we're going to have e raised to some very large positive power. And then as t goes to negative infinity, it's just gonna explode to infinity. Okay, so that's the 3 different regions of convergence. So you can have a right half plane system over here. You could have a strip in the S plane, right? Like this one is here. And if the that would have to be a system with multiple poles. If you only had one pole, you're either left half plane or right half plane. And when we say right half plane, we don't necessarily mean symmetric about the j omega axis. We're just saying that it's going off in the right or it's going off in the left, or in this case we'll have a strip. And then our anti-causal system, well, that's a left half plane system. Let's put that LHP over here and not over on the right. So that's your region of convergence. Now, in order for it to be stable, the j omega axis has to be included. And if it's a linear time invariant system, then it's a causal, and it's going to be right half plane. Okay, so I hope this video helps. Let me know if you have any questions. Thank you.